Next, we have this interesting result coming up. How do we determine whether 2 points are on the same side of a plane or on the opposite sides of a plane? So I've given this topic the name two sides of a plane. Now once again, its derivation is very lengthy. So this is one of those things once again which you just need to actually remember and use them directly in problems. So it's sort of a technique that I'm giving you more than a concept. So here you have this plane whose equation is given to you. You have 2 points whose coordinates are given to you. Now what's happening here is this plane extends in all directions. So what can happen is, there are two cases possible. One is both your points are on the same side of the plane, and the second case is you might have a point on this side and this on the other side of the plane, right? So both cases are possible, one above, one below, or both on the same side. Now the quantity which determines that is this. So what you do is basically you put up this point in the plane, and you take the ratio, right? So if this ratio is greater than 0, what have you done? You're basically, instead of x, y, z, you have actually put this point in the equation of the plane, and then that divided by you have put this point in the equation of the plane. If that ratio is greater than 0, so it will give you a number, right? Once you put in all these quantities, you'll get some number. If that number is greater than 0, then P and Q will lie on the same side, and if that number that you get after putting is less than 0, then they'll lie on the opposite side. Now this has an extremely lengthy derivation. So we're not even going into that because I don't find it very useful. So it's obviously good for the understanding and all, but like it's not very useful for other problems and even for this. So you just have to remember this result. So you can actually write this as P11 divided by P22. So P11 means I'm putting point 1 in the plane, and P22 means I'm putting the point 2 in the plane. So if your P11 by P22 is greater than 0, then 1 and 2 lie on the same side, and if a P11 by P22 is less than 0, then 1 and 2 lie on the opposite side. This is more like a result that you need to remember, and you'll be using this in a lot of problems directly. So with this, we are actually done with all the topics as far as planes were concerned. Let's now move on to the last small subtopic called spheres in 3D geometry. So let us now look at the equation of a sphere. So sphere is also a 3D figure or a 3D shape to which I can write an equation too. So this looks like a circle, but don't confuse this as a circle. This is actually a sphere which is having 3 dimensions, right? So every point on this sphere, if I'm able to get the equation of all the points, that means I've got the equation of a sphere. So equation of any geometrical figure is actually the collection of the points on that figure. So I'm taking a general point here whose position vector is r bar. So position vector r bar means you start from origin, go to that point. This vector is r bar. Start from origin, go to this point. This is c bar. Let this be the center of the sphere, and let the radius of the sphere be a. Right. So the vector, this pink vector, is the vector which actually starts from the center and goes to the point. That is the general point that I've taken. So this is basically your c r bar, which starts from c and goes to r. So I can write this as OR bar minus OC bar, and that's my R bar minus C bar, right? Now, if I take the dot product of this R bar minus C bar with itself, so I've taken a dot product of R bar minus C bar with itself. So A dot A, if I do, that's nothing but mod A square, right? If I take a dot product of a vector with itself, I get its magnitude square. That is what I've done here, R bar minus C bar mod square. And R minus C mod is basically the length of this pink line, and I'm calling it as A. That is the radius of the sphere. That's A square, right? So this is the vectorial form. This itself is the vectorial equation of the 3D sphere that I'm talking about. After having seen so much of vectors, this should be a cakewalk for you. Now let me derive the Cartesian form of the same thing. So basically r bar, let it be your xi plus yj plus zk, basically the coordinates of this point x, y, z, right? And let the coordinates of the center be c1, c2, c3, right? If the coordinates is c1, c2, c3, then this position vector c bar is c1i plus c2j plus c3k, right? Now what I'll do is I'll just substitute these two quantities in this very same formula, right? So I've got this, and I'm taking the dot product of this vector with the same vector, so taking the dot product of this vector with the same vector, right? And that's equal to a square. Now once I carry out this dot product, I finally get this expression. So this is basically the Cartesian equation. If you're able to see anything of this form, remember this is a sphere having center c1, c2, c3 and having radius a. So you should be able to correlate this equation to any figure that you see. If I expand it further, then I will get this. And this is also a very useful equation, because sometimes you have equations given like this. Sometimes you have an equation given like this: 2x square plus x square plus y square plus z square plus 2 ux plus 2vy plus 2wz plus some k square is equal to 0. You might get something like this. So always relate this particular equation that's very commonly seen to this equation. Remember, in this equation, what is my center? This is the center, right? C1 is the center. So the coefficient of x is minus 2 times center, is minus 2 times the x coordinate of center basically. So if I divide the coefficient of x by minus 2, I'll get the x coordinate of center. So what is the x coordinate of center from this? It is minus 2u by 2, right? Or basically 2u by minus 2, which is minus u. So the center for this sphere is minus u minus v minus w, right? If you just correlate this equation and this equation, right? And from this you can also go get the radius as well, because this is c1 square plus c2 square plus c3 square. So here u square plus v square plus w square is something like this, and that minus the radius square is equal to this constant, right? So c1 square plus c2 square plus c3 square minus a square is some constant. Here that constant is k square. So here that constant is k square, and this k square is actually the sum of the squares of the coordinates of the center minus the radius square, right? That's very evident from this equation. So obviously the radius formula also can be got, you can actually get it from here, and that's basically u square plus v square plus w square minus k square under root. So you can always relate this equation to this equation, and that's how you will deal with 3D geometry, 3D spheres in 3D geometry. This is all about the equations of a sphere in both Cartesian and the vectorial form. Let's move on to the next subtopic in this particular thing called 3D spheres.